let's look at the first page, sample research question. Let's assume that a math test was conducted for freshman students at ISU. The scores of this math test, they are normally distributed. That means if we are, remember we are using z-scores. If we are using z-scores, we are still talking about this normal distribution. So the scores from this exam we took here, they are normally distributed with the population mean mu is 60. So these are the information you will always be given. Information on the population mean and standard deviation is 8. So population mean mu and standard deviation 8. Now we as researchers, we want to know if we offer a special tutoring technique, how that will have any effect on this math test. This math test, they are talking about where the population mean or the average was 60 out of 100 and the standard deviation was 8. That was offered to all freshman people here without any special tutoring. Now we are saying that what if we offer a special tutoring with all these freshmen, then they take the exam, so we'll create a sample of 100 people. They will be offered this special tutoring, they will take the exam, and then you will see how, we will try to find out how that special tutoring had any effect on this exam score. That's the idea. Are you guys with me so far? So the exam was given. The average was 60 out of 100. That's the population mean mu. Standard deviation was 8. That was done. Now we are going to offer a special tutoring to find out whether it can have any effect on this exam score. So we selected a random sample of 100 students, offered the tutoring, and then they took the same math test again. From this test, now we are talking about a sample size of 100, and X bar, or in our book, remember for mean they used M in our textbook. So from this sample of 100 people, we found out that the mean or the sample mean score was 70. Now the question is, does the sample mean 70 differ enough from the population mean was 60? So is that difference between the population mean and the sample mean, is it a big difference to make any kind of a conclusion that the tutoring really had any impact and made the difference? Can we make that kind of a conclusion? So first thing is, when we are using these kind of things, we have to have a level of significance decided, and that is denoted by the sign alpha. And normally, either we use alpha equal 0.05 or we use alpha equal 0.01 or 0.001. Rarely we use, no, 0.1. Rarely we use at 0.001. Now, before we do anything, let's look at this page where it says at the top, steps for hypothesis testing. Let's look at this page. Because these are, before we can do any kind of hypothesis testing, we have to go by these steps. So first step, we have to formulate a hypothesis. Again, we are talking about null hypothesis and alternate hypothesis. So we are talking about H sub 0, that's the null, and H sub A or H sub 1, that's the alternate hypothesis. So the null hypothesis will be the tutoring does not have any effect on the math test. In other words, the null hypothesis will be there is no significant difference between the population mean and the sample mean. It should also state that if any difference is found, then that happened due to chance or random sampling error. So, remember what we have. We did this math test first, then the average was 60. The population mean mu was 60. Then we took a sample of 100. We offered that tutoring to these people. Then they took the test and their average was 70. So the population average was 70, but sample average was 70, but the population average was 60. So when we are going to write this null hypothesis, we are going to write as that the population mean what the information we have. H sub 0 equal mu, H sub 0 is mu equals 60. That's the information we have. But based on our special tutoring and based on this sample mean, if we are saying that the special tutoring made any difference, then the alternate hypothesis will be mu is not equal to 60, because it was 60 before the tutoring. After the tutoring, the population mean mu cannot be equal to 60. There has to have some kind of impact. Are you guys with me so far? Lost? Anyway, please. So, as I said before, next line, if you look at the last line in first section number 1, through hypothesis testing, we either reject or accept the null hypothesis. Now, another issue is when we are doing this calculation for hypothesis testing, or we are writing those hypotheses, then there is something called directionality. And in these notes, the first one, H sub A, I wrote it as mu not equal to 0, alternate hypothesis. When you see this sign, not equal to, right away you will know that it's called non-directional test. Non-directional means you have to look at each side, each tail of this normal curve. That's why it's called non-directional. It's not giving any direction. It exists on both sides, both tails of the normal curve. And that means you are talking about a two-tail test. This is the right tail, this is the left tail. Whenever you see this sign, not equal to sign, you will automatically assume that you are talking about a two-tail test. One is the right tail, the other one is the left tail. So two-tail test is always done for non-directional hypothesis. But if it is given a direction, then it will be a one-tail test, depending on what kind of direction is given. For example, if it is given you this kind of direction, which side of the normal curve you are, which tail you are looking at? Left tail. If it is giving you this kind of direction, then you are looking at the right tail of the normal curve. That's why these two are called directional hypothesis. So directional, you will either have a less than or equal to sign, or more than or equal to sign. So this one is non-directional, meaning two tail. This one and this one, they are one